Well, okay. Good afternoon, folks. Is this thing working? Maybe start it. So give me just a second to get the doc cam synced up, and we will get started. Still no dice. Camera. Beautiful. Okay. We're just going to be brave and share the whole screen. There it is. Looks like there's only a few folks here, so I might give just a minute or two longer for other folks to arrive. Welcome to the last week of MAC 1147. You're almost there. Last week we talked about parametric curves and talking about polar coordinates, parametric curves, all that good stuff. There is one final topic that I do like to get into this course when I can, and since it seems like we can, I think we ought to, but I don't want to overwhelm either, and I would rather cover the stuff that we need to cover well than try to extend into extra stuff. But the very last bit of material for this course that is like necessary is sequences and series. Where did Zoom go? All right, meeting controls. Okay. So the binomial theorem and the geometric approach to conics, not super necessary. Neither of those play a huge role in the calculus sequence, although the binomial theorem is a useful trick. But sequences and series are hugely important, not just for calculus, Calc 2 especially, where they make up about a full third of the class, but also for the foundations of analysis. All semester we've been messing around with the real number system. The truth is that the real numbers are a much weirder place than they usually get credit for being. I think, oh, okay, it's a number line, right? And somehow that makes it all make sense. But the number line is a weird goddamn place. If you start throwing darts at the number line, the probability that you ever hit a rational number, that is a number like 1/2 or 5 or 2/3, is 0. It is a probability 1 event that the dart will land on an irrational number. So the vast majority of that number line is made up of weird shit, like the square root of 2 and pi. And to really try and get a feel for how you can have a mathematical object like that, you need to understand sequences. So it turns out that the real numbers, if you want to come up with a rigorous definition, that is a definition that doesn't rely on like waving your hands and drawing a picture and saying there aren't any gaps, requires either the study of Dedekind cuts, which are wholly more complicated objects having to do with suprema and infima, or sequences of rational numbers, and that's the piano axiom approach. That's the approach that most people would take. So the study of sequences and series is foundational to not just calculus, but to the real numbers in general. And so that's what we're going to spend our last bit of energy on here. Before I dive into this newer content, though, if there's any material that you guys would like to talk about from the previous week's homework, I would be happy to take a look at a problem or two like that. So is there anything that's been driving us crazy? Oh, do I not have one? Should. Yeah, there it is. We're still feeling mostly pretty good about polar coordinates and parametric coordinates or parametric curves. Okay, I see in the chat here, we can take a look at the 10th problem from homework 12. Let me turn off the key here so I don't spoil it for you guys. It is off, okay, good. So number 10 gives us these, I'll switch back over here. Homework 12, number 10, asks us to sketch the curve of the parametric equations x equals sine squared t, y equals cos t. And they should give us a time domain, a relevant time domain where t runs from somewhere to somewhere. As curve increases, find a rectangular, eliminating the parameter. Where is the t value thing here? Am I blind? No, maybe they don't indicate here. No, okay, so we're allowed to let t run through all real numbers, where negative infinity is less than t is less than infinity. If it's not explicitly restricted, then you can assume that the parameter is allowed to run over all real numbers. The question here, I don't want to make a table, right? I could make a table of values. That's always an option when you're trying to draw a graph. But really what we'd like to do is eliminate the parameter t somehow. And the trick to doing that for this problem, and for most of these problems that involve a sine or a cosine, especially if one variable involves one and the other variable involves the other, is going to be to use some form of the Pythagorean identity, sine squared plus cos squared equals 1. So here, I would say recall. So by eliminating the parameter t, so I would begin by saying recall sine squared t plus cos squared t is equal to 1. Right, that's that Pythagorean identity. No matter what you're plugging in, that's always true, right? So for any number t, sine squared t plus cos squared t is equal to 1. This implies that sine squared t is 1 minus cos squared t. So x of t, which is sine squared t, is the same as 1 minus cos squared t. And this is a nice thing to recall because cos of t is y. So cos squared t is y squared. So this is the same as 1 minus y of t all squared. And if you look at these ends, x is equal to 1 minus y squared. Which is a quadratic equation. Here, x is given as a function of y rather than y being given as a function of x, but that's okay. We can still work with this. There's a bunch of ways to think about it, and it depends kind of on how familiar you are looking at conic sections outside of the situation where y is given as a function of x. This guy you can factor as 1 minus y times 1 plus y. So I know that if y is equal to 1, x will be 0. If y is equal to negative 1, x will be 0. So if y is equal to 1, then x will be 0. In other words, the point 0, 1 is on the graph. If y is equal to negative 1, then x will be 0. In other words, the point 0, negative 1 is on the graph. And then if I want to figure out what the hell is going on in between here, what does the rest of this thing look like? Let me zoom out. Sorry, zoom out. There's a few ways to go about it. I could think of it just as graphing this Cartesian equation, or I could think about letting t run through some values and try to sort it out that way. If we look from this guy, if y is equal to 0, x is 1. So no, in addition to those points, I also have this point, 1, 0 on my graph. What's more, since this gives x as a quadratic function of y, I know that the shape I'm going to be looking at here is like a parabola. And so I can expect that this curve, I'm going to do my best here, but again, you know, my art is bad, is going to be something like this. I don't have the orientation, not yet. And if I was graphing just the Cartesian equation, the graph would of course go on and on forever, just like any other quadratic, you know, any other parabola would extend like that. However, the curve is coming as a parametric curve. X is sine squared, y is cosine. So a bunch of ways to think about this. Cos t is always between -1 and 1. And if I looked at any other part of this parabola, like out here, the y value is either bigger than 1 or down here, smaller than -1. Another way to think about this, as t runs from -infinity to infinity, sine squared of t is always positive. It bounces back and forth between 0 and 1, but I would never get an x value that is negative out of x equals sine squared t. So I would never end up over here where the x values are negative, right? This is like x equals -1. So it's definitely this piece of the parabola that I'm getting. And then the question is, what's the orientation on this curve? So as t, here they said t is running from -infinity to infinity. They didn't give us any sort of restricted time domain. But I could look maybe as t runs from 0 to 2 pi to give myself some orientation. As t goes from 0 to 2 pi, what is x doing? As t goes from 0 to 2 pi, x of 0 is the sine of 0 is 0. And the sine squared of t is going to actually do quite a bit between 0 and 2 pi. It's going to jump up to 1 at pi over 2, and then come back to 0 at pi. But I could say that also y of 0 is cos of 0 is 1. So if instead of letting t run -infinity to infinity, I let t just go from 0 to 2 pi, then this would be the point associated with t equals 0. That would be my initial point. And I would say that the curve is oriented like this. I'll get to this point when t is equal to pi, because the sine of pi, I'm sorry, when t gets to pi over 2, because the sine squared of pi over 2 is 1, and the cos of pi over 2 is 0. And then we'd get down here by pi. But then what's going to happen is we're going to bounce off of this point and come back. So without some restrictions in the time domain, there's no clear orientation to this curve. So you start out going like this, but then you're going to come back. And as t goes from -infinity to infinity, we just bounce back and forth along this thing forever. It's pretty cool stuff, and I can show you what I mean in Desmos. Just like we graphed that cool cycloid with the bouncing dot the other week, we can graph this guy like that. So here, I'm going to let x be sine squared t and y be cos t. And instead of having this, let me see. Oh, hold up. Yeah. T. And then I can do this, and then allow it to animate cos t. So you see what happens there, right? This dot just bounces back and forth on this parabola. Pretty cool stuff, right? And add in the parabola, x equals 1 minus y squared. You see what's happening. So this little red ball that you see bouncing around on this parabola, you can think of that as the ant that's walking along this path. We were able to find out what the shape of that path looks like by eliminating the parameter. That came from the Pythagorean identity, sine squared t plus cos squared t equals 1. And then just thinking about the range of the sine and cosine function. So I know that the range of sine t is -1 to 1, so the range of sine squared t is 0 to 1, and the range of cos t is -1 to 1. So since cos t is my y, I know that my y values have to run from -1 to 1. They can only go back and forth, which means I'm only on this part of the parabola. So to answer the second part of the question as it was given in WebAssign, they want to know, find the rectangular coordinate equation for the curve. That's the x equals 1 minus y squared piece. And then they're also asking to tell them which variable is it that runs from 0 to 1. So along this part of the graph, along this part of the graph, y goes from -1 to 1, but x goes from 0 to 1. So to answer that very last piece there, you just have to look at the graph you end up with and make sure you identify the correct variable x as being the one that bounces back and forth between 0 and 1. Any questions about how we got this curve or how we were able to know the x values that show up there and the y values that show up there? So how did we get this full parabola, and then how did we know to just take this piece? Any questions on that? So I do hope that you guys are enjoying the parametric equations homework. It is cool stuff, and it's stuff that's going to be relevant in your physics classes, in your calculus classes, and elsewhere. The last topic that we're going to approach in 1147 is sequences and series. And for me, number theorist, this is really the best stuff. This is the good stuff. But also to an analyst or to a statistician, this stuff is foundational and crucial. So whatever type of math you're doing, sequences and series underlie it. First, a definition. Sequence is an ordered list of objects, for us numbers. Another way to say this we could also say that a sequence is a function whose domain is a subset of the set 0, 1, 2, 3, and so on. So it's a function whose inputs are only allowed to be positive whole numbers or non-negative whole numbers. It's the same thing as an ordered list, because if I give you an ordered list, like there's a first element, there's a second element, there's a third element, there's a fourth element. Maybe I give you the list 1, 1/2, 1/3, 1/4, 1/5, and so on. This looks like a sequence according to the first definition. It's an ordered list of numbers, right? There's a first one, there's a second one, there's a third one, a fourth one, and a fifth one. It's a list of numbers, and the order matters. This is the same as defining the function f of n equals 1 over n. So you see the two definitions are equivalent. Or the two ways of thinking about the definition of a sequence are equivalent. Here I use the letter n to emphasize that I'm only plugging in positive whole numbers, right? And over here, I don't need any special notation like that. But over here, I don't really have an algebraic definition, and you're kind of leaning on intuition to say, okay, and the list obviously extends on in the same way. So this is actually the notation that we prefer. Presenting a sequence as a list, while not unacceptable, is rarely the most useful way to present a sequence. So let me grab a couple problems from your upcoming homework. And take a look at the sort of things we'll be asking you to do. When you're first getting to know a sequence, usually you just want to graph them. You want to get good at anticipating what the next value or few values of the sequence will look like. And you might want to get to a place where you can find this expression from this stuff. So where is my, I think in your book, sequences are in chapter 10, no, 12. Okay. So they use the sub notation, that's fine. Yeah, and they define this the same way I do in calculus. Okay. So let's sketch the graph of the sequence above. Now there is a bit of notation. Instead of using this normal function notation here, oftentimes when we're working with sequences, we would write f sub n equals 1 over n, rather than writing f of n. I'm not 100% sure why. The subscript notation, I guess, just takes a little bit less writing to put down on the page. And it allows us to work with the function notation more exclusively for functions of a real variable. So when you see a subscript like this, instead of the parentheses function notation like that, it lets you know right away that you're dealing with a sequence rather than looking at a function whose variable is allowed to run over all real numbers. So if I want to sketch a graph of the sequence above, normally we would label one axis as x. Here I'll label that axis as n because my inputs are now n's, they're natural numbers. And normally I would label my vertical axis as y equals f of x, but here I will label it as y equals f sub n. My pen is dying. The difference between the graph of a sequence and the graph of a function of a continuous variable or a real variable like x is that I'm not going to have a curve here. The graph of a sequence is just going to be a collection of dots because there are no points above, say, 1/2, right? Because the domain of this function, the domain of the sequence, is just the positive integers. There's no part of the graph whose x value is 1/2 or 1/3 or pi or anything like that. So the points on the graph of the sequence are just the points that come from the integer values of n. When n is equal to 1, the sequence fn outputs 1, right? f1 is 1. So I'll do this over here. Since fn is 1 over n, f1, which we would call the first term of the sequence, is 1 over 1, which is 1. And so I have this point 1, 1 right here on the graph. f2 is what I get when I plug in n equals 2. That's 1/2. So that would be right here. F3, what I get when I plug in n equals 3, well, that's going to be 1/3. So that's right around here. Three comma 1/3. F4 would be 1/4. So I have the point 4 comma 1/4, which should be halfway to 1/2, is like right here. And then I would also have 5 comma 1/5. But I don't connect these dots with a curve. I just leave them. That's it. That's the graph of the sequence. Now it continues on and on forever. There's a 6th and a 7th, and those dots are going to get closer and closer and closer to the x-axis. But there's no smooth curve connecting them, just the isolated dots. That is the graph of the sequence. You feel comfy with why the graph of a sequence is just a collection of dots like this instead of a curve? If there was a curve, say, joining these 2 points, then I would be saying that for every number between 1 and 2, there is an output from the sequence associated with that number. But none of the numbers between 1 and 2 are whole numbers. So none of those numbers are in the domain of this function, because a sequence is a function whose domain is a subset of the natural numbers. Make sense? Okay. The sequence I just graphed for you has a special name. It's called the harmonic sequence. So the sequence 1/n is called the harmonic sequence. There are lots and lots of named sequences, a lot of famous sequences. You've probably heard of the Fibonacci sequence. There's the sequence of prime numbers, sequence of even numbers, the sequence of odd numbers. So the we can look at the sequence. So find a sequence which outputs all of the positive odd integers. Well, this is a reasonable game to play. So just like we had a formula for that last sequence, Fn equals 1/n, here I would like to find a formula for a sequence who, instead of outputting ratios whose numerator is 1, outputs just all the odd integers. Let me call this sequence an. So a1 should be 1. a2 should be the next odd number is 3. a3 should be the next odd number, which is 5. a4 would be the next odd number after that, would be 7, and so on. So one common task is to be given a list like this and asked to come up with an algebraic representation for that sequence. Find a formula, right? I think the nice observation here is that 3 is 2 plus 1. 5 is 4 plus 1. 7 is 6 plus 1. And the 4 plus 1 I can think of as 2 times 2 plus 1. This guy I can think of as 2 times 1 plus 1. This guy I can think of as 2 times 3 plus 1. And this guy, 1, I can think of him as 2 times 0 plus 1. So the pattern here is you get 2 times something plus 1, and that something is going up by 1 each time. So there's more than one way to do this. I could say an is 2n plus 1, where n equals 0, 1, 2, and so on. And this would work. This is a sequence that outputs all the odd positive integers. If I need it to match exactly like this, like a1 equals 1 rather than a0 being 1, I could say an is 2 times n minus 1 plus 1, where n equals 1, 2, 3, and so on. This can be simplified. This is 2n minus 2 plus 1 is 2n minus 1. So really, exactly as it's given here, that's this guy. But you'll often see both of these as your generic odd number, because both of those are sequences that output the positive odd integers. They have a different domain. When I want to write all the odd positive integers like this as 2n plus 1, I have to let my domain be 0 to infinity. Again, just taking the whole numbers there. And if I want to write my collection of all odd positive integers as 2n minus 1, I have to let n run from 1 to infinity. And there is a special notation for that. Special notation for sequences with a specified domain. So for that first guy, we can package the information an equals 2n plus 1, n equals 0, 1, 2, all the way off to infinity in the box I put curly braces around the formula. And then down here, I put the starting value of n. So here, n is starting at 0 and running to infinity. So this is another way of saying both of these things at once. Similarly, we can package the information an equals 2n minus 1, where n is equal to 1, 2, 3, and so on, as curly braces 2n minus 1 with a little n down here starting at 1 and going to infinity. So these are the common notation for a sequence. Sometimes you'll be given a formula, an explicit formula like an equals this, and then they'll also tell you where n starts separately. Sometimes they'll write everything together in one little block like that. Questions on the notation? Okay. So returning to some other special sequences. One family of special sequences the family that the Fibonacci sequence belongs to are called recursive. The other two that we're going to study are arithmetic sequences and geometric sequences. Geometric sequences are going to be very important in your calculus class. But I think recursive sequences are the most fun ones to play around with at first. So let's look at those. A recursive sequence is one in which the nth term of the sequence is given not explicitly with a formula, but in terms of the previous terms of the sequence. So like our very first example, here, the nth term of the sequence is 1 over n. We're given a formula for it. But in a recursive sequence, rather than being given a formula for the nth term, I'm given a formula that tells me how to calculate the nth term from the previous terms. So an example of a recursive sequence is the factorial. Maybe I'll use an here again. So the sequence, so let's find the first 5 terms of the recursive sequence defined by the rule a0 equals 1 and an plus 1 is equal to n plus 1 times an. So this is called the initial condition. And this rule, which tells you how to get the n or the n plus first term in terms of the last guys, tells you how to get the next guy in terms of the previous ones. This is called the recursion relation. So I know what a0 is. a0 is 1. How would I find a1? Well, all I really have to go on is this. And if you plug in n equals 0 here, you find that a1 is 0 plus 1 times a0. Okay, well, a0 was 1, and 0 plus 1 is 1, so this is 1 times 1, which is 1. How do I find a2? Again, I go back to this recursion relation. If I plug n equals 1 into that, then I get 1 plus 1 times a1. So a2 is 2 times a1. And a1 I just calculated is 1, so this is 2 times 1, which is 2. And if I wanted to calculate a10, I would first have to calculate a9, because a10 would be defined as 10 times a9. So let's do a few more. a3, if I plug n equals 3 into my recursion relation, I get a2, right? Or sorry, if I plug in, so to get a3 out, I plug in n equals 2, because this is an plus 1. So a3, I plug in n equals 2, this is 2 plus 1 times a2. Well, 2 plus 1 is 3, So this is 3 times A2, and A2 is 2, so this is 3 times 2, which is 6. And A4, I was asked to find the first 5 terms, so A0 through A4, that's the first 5. I would find by plugging n equals 3 into my recursion relation, I find that that's 3 plus 1 times A3. 3 plus 1 is 4, so this is 4 times A3, which is 4 times 3 times 2, or 4 times 6, which is 24. So this is one example of a recursive sequence. This one is called the factorial. And if you've taken any statistics or you've done any counting problems, combinatorial stuff, then you'll see that the factorial is very important there. N factorial, the nth term of this sequence, turns out to be the number of ways you can reorder a group of n things. So for example, there's 52 cards in a deck of cards. The number of possible ways to shuffle those cards is 52 factorial. It's the number of ways you can order 52 objects. Do one more example of a recursive sequence, and then we'll look at arithmetic and geometric sequences. The classic example of the recursive sequence is the Fibonacci sequence. So find the first 5 terms of the sequence defined recursively as, I'll call this capital F. So capital F0 is 1, and Fn plus 1 is equal to, we also need F1, yeah, F1 is 1. Capital Fn plus 1 is Fn plus Fn minus 1. So again, these are my initial conditions. And this is my recursion relation. I have F0 and F1, but if I wanted to find F2, according to this rule, I get that by plugging in n equals 1. So F2 is F1 plus F0. Both of those are 1. So this is 1 plus 1, which is 2. F3 would be F2 plus F1. F2 I just calculated, that's 2. And F1 is known as 1, so this is 3. F4, the 4th Fibonacci number, I don't know what it is off the top of my head, but I know it's the 3rd Fibonacci number plus the 2nd Fibonacci number. F3 plus F2. Right? To calculate the next guy, you add up the previous 2. What was F3? It was 3. F2 is 2, so this is 3 plus 2 is 5. We'll do one more. F5 should be F4 plus F3. F4 was 5. F3 was 3. So the next Fibonacci number is 8. And this sequence 1, 1, 2, 3, 5, 8, 13, and so on, that's called the Fibonacci sequence. One very natural question to ask about recursive sequences is, can you find a formula? Instead of working with the recursion relation, is it possible to find an explicit formula, just a straight algebra formula like 1 over n or 2n plus 1, that will give you the nth Fibonacci number? The answer to that question is sometimes. Sometimes it's very easy, sometimes it's very hard. In the case of the factorial sequence that we just played with, this one, I can find an explicit formula. It turns out here, so just by playing around with this, right, I've got 2 times 1, 3 times 2 times 1, 4 times 3 times 2 times 1. it turns out here that an is going to be n times n minus 1 times n minus 2 times all the way down to 3 times 2 times 1. So this is an example of a recursive sequence where you can solve explicitly to find a formula for an. It is also possible to find a formula for the nth Fibonacci number, but it is nowhere near as nice. It's much harder. The Wikipedia page for these is good. The usual trick is to play around with something called a generating function, but that requires power series, which requires Calc 2, so it's well beyond the scope of this class. But it is possible. It is possible to find a formula. If I remember right, it's something like Fn is 1/2 phi to the n plus phi to the negative n, where phi is 1 plus the square root of 5 over 2. But I'm not sure. That's about what I remember, but I haven't gone through that process in a long time. So these are recursive sequences. Right? A recursive sequence is a sequence where to get the next term, you have to have computed the previous terms, and then that next term is calculated by combining the previous terms in some way. Maybe you add them like here, maybe you multiply them like in the previous one. Sometimes you do different things. It all depends on this recurrence relation. The next important family of sequences are arithmetic sequences. I'm going to go ahead and turn the fan on here because it's getting pretty warm, so give me just 1 second. Okay, so the next important family of sequences for us to look at are arithmetic sequences. This is the sequence version of a linear function. So remember, a linear function is a function whose rate of change is constant, right? And we normally think of that as a slope. For arithmetic sequences, we don't like to use the term slope because the graph isn't a line anymore, right? It's still just a collection of dots. So instead, we talk about what's called a common difference. So an arithmetic sequence is one which can be expressed as one, let's say, one in which to go from a given term to the next term we add a fixed constant. So like in our sequence of odd numbers, 1, 3, 5, 7, 9, 11, that is an arithmetic sequence because to go from one term to the next term, we add 2, right? 5 is 3 plus 2, 7 is 5 plus 2, 9 is 7 plus 2, and so on. So that is a sequence which can be expressed as an equals A0 plus n times d. So your variable here is n, A0 and d are both constants, and the name for d is the common difference. So A0 we would call the starting term. And d we call the common difference. D is the step size, right? So we say an arithmetic sequence is one where to go from a given term to the next, we add a fixed constant. D is that fixed constant. So if you were to subtract any two consecutive terms of an arithmetic sequence, you'll get the same number, D. And A0 is called the starting term because it's the term with which the sequence starts. That is fairly intuitively named. So an example of an arithmetic sequence, let's find a formula for the sequence which begins, maybe A0 is 5, A1, let's say is 9, A2 is 13, A3 is 17, and so on. But what I see is that to get from here to here, we had to add 4. To get from here to here, we had to add 4. To get from here to here, we had to add 4. So this looks like an arithmetic sequence. That is a sequence where to get from one to the next, we add a fixed constant. This appears to be, so I'd say AN appears to be an arithmetic sequence with common difference d equals 4. Because to go from one term to the next, I'm adding 4. The next term of the sequence would be 21, and then 25, and then 29, and so on. Now the problem asked me to find a formula. And since I know A0 and I know the common difference, D, I can just plug in the formula for the nth term is AN equals A0, which is 5, my starting term, plus n times D. Well, D is 4, so this is n times 4. We could write this as 4n plus 5. And then the only thing we have to remember is to specify where n begins. So I could say, I could package all of this, i.e., this is the sequence. Curly braces, 4n plus 5, where n goes from 0 to infinity. How are we feeling about this notation, these concepts? It's a reasonable place to pause. Questions on this particular example? Questions on the notation here, like the curly brace notation with the n equals 0 and infinity? Comfy with that? Yeah, let's see. What sequence uses big E for the notation? I'm not aware of any sequences that like by default use capital E as the symbol here. Usually for sequences, we use letters at the beginning of the alphabet, like A, B, and C, so like AN, BN, CN. Sometimes if there's a special reason to, like with the Fibonacci sequence, I call that capital FN because Fibonacci is, it's a named sequence. But I'm not aware of any that by default use capital E, or I'm not aware of any special meaning to the notation capital E sub n. Smaller number go on bottom. I am not I am not too sure exactly what you mean by that. So smaller number on bottom. So these numbers down here, the 0 here, the 1, 2, 3, those are the index. That's like the value of the variable. So if I think of this as a function, a of n equals 4n plus 5, then a1 is what you get when you plug in 1 for n. A3 is what you get when you plug in 3 for n, and so on. Oh, for the curly brace notation, yes. Starting value here, ending value here. And all of the sequences we are going to look at least for now, are infinite sequences. So it'll always be n equals whatever the starting number is here, and then an infinity up here. There's one special kind of sequence we're going to look at, which is finite in length today, and those are called partial sums. But yeah, starting number, so smaller number here, bigger number there. Yep. Good questions. Anything else we're wondering about the notation or the concepts here? Okay. So the last important family of sequences that we mentioned are geometric. And a geometric sequence, this is the sequence version, just like arithmetic sequences are the sequence versions of linear functions. A geometric sequence is the sequence version of exponential functions. What I mean by that is, these are sequences a geometric sequence a few ways to think of it is one in which to go from a given term to the next term, we multiply instead of adding. We multiply by a fixed constant. And that fixed constant, just like in the setting of a arithmetic sequence, we call that fixed constant the common difference. Here we'll call this the common ratio. So this is called the common ratio. And we use the symbol R instead of, like, for this guy we called the common difference D. Here we call the common ratio R. That is, geometric sequences are those which can be written, which can be expressed as an equals a naught, the starting term, times r to the n. So we'll look at an example here. I'm going to say find a formula for the sequence which begins with the terms maybe A0 is 2, A1 is 2/3, A2 is 2/9, A3 is 2/27, and so on. So to go from A0 to A1, we're getting smaller. You could think of it like you're subtracting something, but that's not the most natural way to think of it. Because if you compare A1 to A2 and A2 to A3, there is no constant you could be adding or subtracting to get from here to here, and also from here to here, and also from here to here. But what I do notice is that to go from 2 to 2/3, to get from here to here, we multiply by 1/3. 2 times 1/3 is 2/3. And then to go from here to here, we multiply by 1/3, right? 2/3 times 1/3 is 2/9. To go from here to here, we again multiply by 1/3. So this is a geometric sequence with starting term A0 equal to 2 and common ratio R equal to 1/3. If you're given a sequence and you know it's geometric, you can always find the common ratio by dividing any two consecutive terms. Like A1 divided by A0, 2/3 divided by 2 is 1/3. A3 divided by A2, 2/27 divided by 2/9, the 2's cancel, and you get 1/27 over 1/9, which is 9/27, which is also 1/3. So hence the term common ratio. So finally, our formula is two times 1/3 to the n. And you see, if you plug in n equals 0, you get 2. If you plug in n equals 1, you get 2 times 1/3, which is 2/3. If you plug in n equals 2, you get 2 times 1/9, which is 2/9. So the formula works well. Here, n goes from 0. So if I wanted to package this in the curly brace notation, I would say that this is the sequence 2 times 1/3 to the n, where n runs from 0 to infinity. Geometric sequences are kind of the first sequences that are fun. They're the first sequence. Recursive sequences are fun too, but they're too difficult. We can't really learn a whole lot about recursive sequences as a whole, because they can be really, really different. Their behavior is wild. It's all over the place. Depends entirely on the recursion relation. Sometimes they're also very sensitive to the initial condition. So even two recursive sequences with the same recursion relation could behave differently depending on the initial conditions. Arithmetic sequences are kind of boring because they're like linear functions. You know, their graphs all kind of look the same, and they don't do anything special as n gets big. But geometric sequences, they do something pretty cool as n gets large. They're the first sort of sequence where we can talk about what's called convergence. Now in this class, we don't really know what a limit is. So I can't really give you too much to talk about when it comes to limits of sequences and convergence of sequences. We're going to have to keep it rather tame. But I can show you some cool shit. And I'll do my best to keep it accessible. So the big question with sequences is what happens as n goes to infinity. If I put in bigger and bigger and bigger numbers for n, do any of these sequences do cool shit? Now, Desmos, I believe, is capable of playing nice with sequences. So let's graph this guy. And it's going to graph n as a Yeah, I don't know if it's capable of interpreting a variable as a, let's see. Yeah, it's trying. Here you go. So this is graphing the first few terms of the sequence 1 over n. So let me fiddle with this just a little. There we go. So what you're going to see here, that's the first term of the sequence. And slide this out. Is this going to work? Yeah. So we'll zoom in. I don't need n to go all the way out like that. So we're going to look at the first few terms of this sequence. That's our sequence. That is the 2 times 1/3 to the n sequence, graphed for n equals 1, 2, 3, and 4. If I let this keep going, you see those black dots are all getting closer and closer and closer to the horizontal axis. Close this. This is what it means to say a sequence has a limit. I could shift everything up. And you see the same sort of behavior. They're all getting closer and closer and closer to some particular value. What's neat about geometric sequences, so we can answer this question in a meaningful way for geometric sequences. If the absolute value of the common ratio is less than 1, then the geometric sequence a0 times r to the n will go to 0 as n goes to infinity. It's worthwhile to think about why. On the one hand, you can think of this as being like an exponential function. And we know exponential functions all have horizontal asymptote y equals 0. So if you're looking at a decaying exponential, you know those curves all look like this. And so a sequence, a geometric sequence where the common ratio is smaller than 1, those dots will all be glued to the graph of some decaying exponential whose horizontal asymptote is y equals 0. So since the curve gets closer and closer and closer to 0, the dots have to get closer and closer and closer to 0. That's one way to think of it. Arithmetic sequences are boring. They all live along straight lines. So as n goes to infinity, they either go up to plus infinity or down to minus infinity. Some recursive sequences have behavior like this, have a horizontal asymptote, or we would say in terms of sequences, we would say they converge. But it's hard to classify which ones do and which ones don't. So for geometric sequences, if r has absolute value less than 1, then the sequence will converge to 0. That's cool stuff. It's not something that I'm going to beat you guys to death with here because it's technically calculus, but it would be crappy of me to show you a geometric sequence and not tell you that this is the case. Geometric sequences are fun. One of the fun things we can do with them is, instead of just listing terms or finding formulas or asking what is the next term, something we can do in general is to add up the terms of a sequence. Yeah, and this is what Josh was just asking me in the chat. What happens if you see that capital sigma? So this is the start of our discussion on series. So that capital sigma is the notation we use for series. We're mostly interested in infinite series, but we're going to start by looking at finite series. And the key to getting comfortable with this is what's called sigma or summation notation. So some addition problems, addition is a binary operator. Let's start there. The way addition works, you give me two numbers, I apply the binary operator plus to them, and it adds those two numbers, drops out the result. So addition is fundamentally something that is done two at a time. If I'm given a big old addition problem, I have to break it up and add the numbers two at a time until I get the result. It is therefore convenient to have a notation for adding up a whole bunch of shit instead of having to write this plus this plus this plus this plus this. So if I want to add up a bunch of numbers, let's call that first number I want to add a 0. And then to that I want to add a 1, and then to that I want to add a 2, and then to that I want to add a 3. And I want to add a whole shitload of these, so many of them that I'm just going to call that capital N. So here, this is just a number. A0 is just a number. A1 is just a number. All of these are just numbers. The way I'm writing them, it looks like they are outputs from a sequence. It looks like they're terms of a sequence. And indeed, that's usually how we study these things. The way to write the big addition problem in the line I'm going to label star is as, and this is just a special notation that we use for adding up a whole bunch of stuff. You use a capital Greek letter sigma. Sigma stands for sum, like S-U-M, to add up, to sum. And then you specify what you're adding up. So I'm adding up a bunch of things that look like a sub some number, where that number runs from, in this case, well, the first term is A0, so little n is 0 there, and the last term is A sub capital N. This. In other words, this guy is defined to be this. So this is just a shorthand for A0 plus A1 plus A2 plus A3 plus A4 plus A5, da, 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 all the way out to AN. This is called sigma, or summation notation. It's going to take some time for you to wrap your head all the way around this thing. I'm going to look at some examples here, and the first time you see it in the homework, it's probably going to frustrate you a little bit. But I beg you, please be patient, and please, for the love of fuck, learn this stuff. It makes my life so much easier when we meet again in calculus if you understand this sigma notation. And so many unfortunate points are lost, even as late as Calc 2, by folks not understanding this notation. So it is a little bit complicated. It's not super easy, but it's worth your time. To try and get a feel for it, let's expand and calculate sigma n equals 1 to 5 of, let's say, 2n. Okay? So what does this notation say? This notation says I'm going to take this thing and add it up over this range of n. So it says I'm going to take this thing and add it up over this range of n. So what is that? Well, sigma little n equals 1 to 5 of 2n, is 2 times 1 plus, that's when little n is equal to 1. 2 times 2, that's when little n is equal to 2, plus 2 times 3, that's when little n is equal to 3, plus 2 times 4, that's when little n is equal to 4, plus 2 times 5, that's when little n is equal to 5. So the sigma notation is for what's called a series, and it's very different than what we're calling a sequence. A sequence is a list of numbers. A series is what you get when you add up the terms of a list. Here I'm looking at the sum. We would read this as the sum from n equals 1 to 5 of 2n. So that's what you get when you sum 2n, where little n runs from 1 to 5. So it's 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4 plus 2 times 5. It's this thing added up over this range of n. All right, so what is this shit? That's 2 plus 4 plus 6 plus 8 plus 10. So that's 6 plus 6 is 12, plus 8 is 20, plus 10 is 30. Okay. So that sigma operator is a convenient way to write really big addition problems in a little amount of space. We're out of time, but I want to do one more example like this just to let you see it. So if you're desperate to get going, feel free. But this sigma notation stuff is something that I know is challenging, so I don't want to leave you hanging. Let's expand and calculate sigma n equals 0 to 4 of n squared. So this means I'm going to plug in 0, 1, 2, 3, and 4 to this formula, and then I'm going to add them all up. So that's 0 squared plus 1 squared plus 2 squared plus 3 squared plus 4 squared. This is just a shorthand for this whole thing. Oh, this takes up a lot less space. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. So this is 5 plus 9, which is 14. 14 plus 16 is 30, 31, 32. So 20 plus 10, oh no, it's just 30. Yeah, oh, that's funny. This came out to 30 also. That's just a coincidence. That was not fun. The next few things we're going to do as we go down the road, we're going to discover formulae for sigma n equals 1 to capital N of n, sigma n equals 1 to capital N of n squared, and sigma n equals 0 to capital N of a geometric sequence. All right, and we're going to start playing around with those. And that will lead us towards asking what happens if this number goes to infinity? What happens if I want to add up infinitely many numbers? Turns out to be a really interesting question. These are called infinite series, and most of the time when people talk about series, they're referring to infinite series. It'll also be the right setting for us to talk about the binomial theorem and a little bit about induction if we have time, but I'm not sure we will. We'll have to see. So this is where I'm going to stop the lesson for today. I see there is something here in the chat. Let me take a look at that. Let's see, exam 3 note. So if you, oh wait, no, yeah, different class. I'll just respond to that in the chat. Yeah, so we can stop the lecture here. I'll go ahead and stop the recording. If you have anything that you would like to talk about, feel free to hang around, but otherwise you are free to go. And I will see you guys tomorrow for more talk of sequences.